Okay, so today we're going to be starting the real kind of mechanical stuff of physics, right? We're going to start off pretty basic, and we're going to be looking at the difference between the two kinds of measured quantities that we can have in physics. Okay, the two kinds of measured quantities that we can have are scalar quantities and vector quantities, right? They look at things they look at the same things, but they look at them in different ways, right? So, for example, if you're rocketing down the Deerfoot at 130, you're probably going to get pulled over and get what? A ticket. You're going to get a speeding ticket, okay? Because your speed was 130 kilometers an hour, right? Now, does the police officer care which direction you were going? Well, actually, you probably would if you were on the wrong side of the road, okay? But we're assuming you weren't going 130 against traffic on the opposite side of the Deerfoot, okay? Because you probably wouldn't get a ticket then. You'd get, arrested, basically. Yeah. All right. So assuming that you were on the right side of the road, he's just giving you a speeding ticket. He's saying your speed had a magnitude of 130 kilometers per hour, and that's against the law. Okay. He's not giving you a velocitying ticket. But we seem to think that speed and velocity are the same thing, because up until now, they have been for you. Okay, velocity and speed were essentially the same thing, but in fact, they're not. Speed is a scalar quantity, and scalar quantities convey no direction. They just have a magnitude. How big are they? Okay, if it's speed, it was 130 kilometers per hour. Right? Mass is another scalar quantity. Okay? When you tell someone your mass, you don't say, 70 kilograms right, because that doesn't make any sense. Okay? Your mass doesn't have a direction. That's just how much of you there is. Okay? It's a scalar quantity. Right? Whereas if I'm talking about something like displacement, displacement is a vector quantity. It's how far and in what direction you have gone from your starting position. Okay, so if I've, let's say, gone hiking and I ended up, walking 5 kilometers east, okay, that would be my displacement, 5 kilometers east. But the distance I traveled was just 5 kilometers. So they look at the same thing, distance being scalar, didn't mention which direction, okay, and displacement being vector, and adding on, okay, a direction to that. Now, when you're just dealing with a one-way trip, it's pretty easy. But if I've got a there and back trip, then it starts to get a little different, and that's what we're going to cover today. All right, so there's many ways of measuring how far apart and how fast objects are going. Okay, we need to be able, this is kind of the big one, to differentiate between distance, displacement, speed, and velocity. All right, not so much because I'll have a question on a test that's, a multiple choice of which of the following is a scalar quantity, although I might do that, but more in if I have a written response question, and it says, here's some information, calculate the velocity of the object. Well, you're going to calculate velocity differently than you would calculate speed, and as a result, it's important that you know the difference, okay, so that you solve the problem the right way. Everyone follow me there? Yeah. All right, and then we're going to solve problems, lastly, related to uniform motion, and we're going to be using these two formulas. V equals d over t and v equals d over t. You're probably going, Coder's day off was way too good yesterday. He's crazy, that's the same formula. Actually, it's not, because the little arrows over top of the v and the d here mean that these are vector quantities. Okay? This formula has scalar quantities in it. All right? So in this formula, the v would stand for speed, and this would stand for distance. Whereas in this formula, the v would stand for velocity. And in this formula, the d would stand for displacement. What does the t stand for? Time, yeah. How come it doesn't have an arrow over it in the second formula? What's that? Time's always the same, Daniel? Same for both. Can time run any direction? No, time can only go forward, as far as we know anyway. If you have a time machine at home, we got to talk. There's a few things in my life I would do differently. Okay, yeah. All right, so time is a scalar quantity because really it only goes one way. Okay, our perception of it can change, but time flows and flows constantly. Okay, and it always flows forward. You can't go back in time. All right, so time is always a scalar quantity. That's why it doesn't have an arrow over it in either one of those. So T is for time. All right. So if we're looking at this situation here, okay, this is a 8-day backpacking trip I did with my father about 10 years ago. If you've ever done any hiking or anything like that, you'll notice that we've got a really messed up way of talking about distance in North American culture. Okay, I'll give you an example. I'm going to ask Luke how far it is to Edmonton. Okay, that's only the 5th time in all of my years of teaching, which is more than I care to admit, that someone has actually given me the right answer. Okay, Luke said 300 kilometers. How many of you were thinking 3 hours? Yeah, most hands go up. Okay, because that's how we think of distance in North America. We think about it in how long it will take us to get there, not in actually how far away it is. All right, that's because of the modes of transportation that we use. Okay, the modes of transportation we use, we get in a car, we get on the road, we go to where we're going. We travel the speed limit, we know about how long it's going to take. Well, there's a problem with that. Can you always go the speed limit? No. Okay, we're getting into that time of year where there's going to be times where you have to go considerably slower than that. Okay, and then as a result, how long it takes to get to Edmonton is different. How far Edmonton is away is always the same number. It's always about 300 kilometers. Last time I checked, Edmonton didn't get further away. Okay, that's a number that is consistent. Right? However, the time is dependent on how fast I'm going, and that number could change. Everyone follow on that? Okay, so give you some examples here of how that's kind of messed up. Not on this particular trip, but on another backpacking trip I did with a buddy of mine. We'd been hiking all day. We had almost a 30-kilometer day that we had to finish, and it was getting to be about 4:30 in the afternoon. We'd started at 6:30, and we were dead tired. And we're thinking, man, we must be lost because we should have been there already, and we should have been at this campground. And then we see this guy come hopping up this hill, and he's just motoring, coming the other way. And we didn't think about it at the time, but in hindsight, we realized it. He was wearing like army fatigues and had like a big giant pack, army boots. He was probably like a Navy SEAL or something. Okay, like this guy was practically running, wearing 80 pounds of gear, and yeah, he was an incredible physical specimen. Anyway, we asked him, where did you come from? Did you come from Tumbling Creek Campground? And he said, yeah. Oh, it's real close. It's like 10 minutes that way. We're like, oh, sweet, we're not lost. It's only 10 minutes from here. Yeah, 45 minutes later, we finally got there, and we were cursing this guy something fierce. Okay, what did we not realize? He was running. He was in way better shape than we were, and he'd just started. We'd been hiking all day. Not that that's any excuse. He was in way better shape than we were. Okay, and he was going uphill. We were going downhill. That was the really sad part. So yeah, the way he described how far away the campground was wrong. He described how long it took him to get there, which is how we describe things in North America, stupidly. Okay. Time is dependent on how fast you go. If he'd have seen us walking for about 3 minutes, he'd have gone, it'll take you 4 hours. Okay? You'll be there in 4 hours. It'll be dark, but you'll be okay. Okay? No, he would have, we just can't talk about how far something away is something away. Bleh. How far away something is in terms of time, because it's dependent on other things. All right? So if I'm standing right here at Seldom Inn Campground, and I want to get to here, Snake Indian Falls Campground, as I leave the campground, there's a sign on the trail, and it says Snake Indian Falls Campground, 27 kilometers. Now, that 27 kilometers is assuming I'm going to do what? Yeah, I'm going to follow the trail because it's 27 kilometers this way. It gave me a scalar quantity. Right? It didn't tell me which direction it is. It basically assumed I would logically follow the trail and it would be 27 kilometers. All right? And that's the same thing that all of our road signs do. They tell you Calgary is 34 kilometers on this road. All right? If you had a helicopter, it would be less because you would be able to go in a straight line from A to B. Okay? I mean, if I was, able to do this, it wouldn't have been 27 kilometers. It would have been more like 18 maybe. Okay? It would have been a lot less because a straight line is, of course, the shortest distance between 2 points. The problem is that's impossible. This is a glacier, this gray part. Okay? These are rivers, and there's canyons and all other manner of disaster along that path. That's why there's a trail that goes this way. Right? So we assume a lot of times with scalar quantities that people are going to follow a certain path. We give them vector quantities if they're able to go in a straight line from one place to another. Does that sort of make sense? Okay, so they each have their use, right? And one isn't more accurate than the other either. There's always this impression that vector quantities are more accurate, but they're not. Okay? I could have a less accurate vector description. If I said this sign, the sign that said how far it was on the trail, maybe it said it was 27.8 kilometers. Okay? But this way, in a straight line, it was 19 kilometers. And we'll say at 38 degrees north of west, okay, given a compass direction. Which one of those is more accurate? No, this one's more accurate. It's measured to the nearest tenth of a kilometer. This one's measured to the nearest kilometer, right? It's got no decimal there. Okay, so this one is accurate to plus or minus 1 kilometer. This one is accurate to plus or minus 0.1 or kilometers or 100 meters. This is a more accurate number. It was measured more accurately. Okay, everyone follow me on that? Is this number more descriptive? Yes. This number, though, doesn't have to be descriptive. It assumes I'm going to follow the trail. Okay, so it doesn't need to be as descriptive. Right? So don't get the idea that vector quantities are always more accurate. They're not. Okay, it's how well did you measure them. That's what determines their accuracy. Okay, so let's say there was no trails here, no trails on this map, and I still needed to get to all of these campgrounds, okay, along the way. Am I going to want scalar descriptions or vector descriptions then? I'm going to want vector descriptions, yeah, because I'm going to have to use a compass, and I'm going to have to try and walk straight lines, okay, along the path. Now, obviously, avoiding, okay, whatever manners of disaster there are, right? I would maybe have to plot a route that would go maybe something like that, or okay, and follow a different way. Okay, so scalar descriptions are useful provided there are defined routes to follow, and scalar descriptions vector descriptions are more useful if there are no trails. Okay. So, if we say Calgary's 40 kilometers away, that's a scalar description. That's the distance that you would have to travel to get to Calgary. You may have to travel several different directions along that 40-kilometer path. Okay, so if we're doing this, you can see that we change directions lots of times because we got to go around all the natural land formations and human-made structures that have been put in the way. Okay, the Deerfoot just doesn't go in a straight line. Right? It's got to find good places to cross rivers and things like that. Right? So it's 40 kilometers if I stay on the Deerfoot. But if I went like this, okay, it would be a little bit shorter. Okay? It would be a straight line, but then I would also have to say, here's the direction you need to head in. So if I had a helicopter, okay, then I would say, all right, it's a few degrees west of north, maybe, I don't know, about 10 degrees or so, something like that, about 10 degrees west of north. Okay, head in a straight line and go this far, 10 degrees west of north. Right, then I could get there. All right, everyone okay with that? Okay, another example. Yeah. This is my house. Okay, and this is Sprawlmart, otherwise known as Walmart or Wally World, whatever you call it. Okay, all right. if I want to go from my house to Walmart, okay, it's about 4 kilometers, okay, but I can't travel in a straight line from my house to Walmart. So, you know, I get out of my house and then I follow the road, and then the road turns, and you know, I follow Southridge Drive or whatever, and I go across the river, and then I got to make other turns and things like that, right? And you go into the parking lot at Walmart, okay? So let's say that along that black line, it's 4 kilometers to Walmart, okay? Let's say it takes me a half an hour to walk there. How fast am I going? I was actually looking for a number. Sorry, I should have been more specific. Okay, it took me a half an hour to walk 4 kilometers. What's my speed? Right? 8 kilometers an hour. Okay, so what Maria just did in her head is this. Okay, V equals D over T. Speed is distance over time. I went 4 kilometers in a half an hour. Okay, probably what Maria did in her head is multiplied that by 2 to figure out how far I would have gone in an hour, right? Yeah. But that's the same as doing this. 4 divided by 1/2 is 8 kilometers per hour. Okay, not a hard calculation, right? All right, so that's my speed. These are all scalar quantities. They don't mention anything about direction because there are many directions that I traveled in getting from my house to Walmart. Now, if I had a helicopter, I wouldn't shop at Walmart because I could afford to shop way better places. Okay, but I would follow that path instead. Straight line, way shorter. Okay, let's say it's, I think the number I have in your notes is 2.8 kilometers, is that right? Okay, 2.8 kilometers. And let's say I also have to have a direction now because this is a straight line and I need to know which direction to go. What do I have in there? It's 30 some degrees or something. 38 degrees. Do I have west and north? I have north and west. Okay, well, we'll say it's west and north. It doesn't really make a difference for this one. This one is measured west of north. If I was doing it the other way, I would have drawn the triangle like this. Okay, and then this angle would be 38 degrees north of west. You know what? I'll just do that because that's the way it's in the notes there. Forget I have this blue triangle at all. Okay, so if I'm walking to Walmart from my house, 38 degrees north of west, 2.8 kilometers. Okay, what's my velocity then? Still the same trip. Okay. In the end, if I could have gone in a straight line when I walked to Walmart, if I could have gone in a straight line, that's the way I would have gone. Okay, 2.8 kilometers takes me a half an hour. What's my velocity? Do I calculate it the same way? Yeah, okay. Velocity is my displacement over my time because in the end, this is what I did. Yeah, I followed this road, but I ended up 2.8 kilometers in a straight line from my house. Okay? So velocity and speed and distance and displacement talk about the same trip from different points of view. All right? Is everyone okay with that? All right. So I went 2.8 kilometers at 38 degrees north of west. All that has to be included. And I did that in a half an hour. Okay? Because that's how far I ended up from my house. All right, so in the end then that means that my velocity was 5.6 kilometers per hour at 38 degrees north of west. Always have to have the vector on there. Now, you're not going to have to do compass directions that are degrees because then it would bring trigonometry in, okay? And we can't guarantee that you've done all the math stuff with that yet, okay, if you haven't taken math this semester, okay? But you will do it in Physics 20. So there's my overall velocity for the trip to Walmart. Okay, what's that? Well, you're right, it would have been more of a leisurely walk, but here's the thing. I wasn't actually able to do this. But a person might ask me, what was your displacement, even though you actually went 4 kilometers? How far were you actually displaced from where you started? Okay, well, displacement always deals with a straight line. Okay, this is how far in a straight line I ended up from my house. All right, it's a different number. Okay, now let's say I walked home. It followed exactly the same route, just reversed it and went all the way back home. How far have I gone? 8 kilometers, just the same distance back. Okay, now I've gone 8 kilometers and I walked at exactly the same speed, so it took me another half an hour. So is my speed still 8 kilometers per hour? Yeah, because it's exactly what I did. My total distance is 8 kilometers, my total time is 1 hour. What's my velocity over the whole trip? So I've gone there and back. How far am I displaced? No. Okay, remember, here's the definition of displacement. Displacement is how far in a straight line you have gone from where you started. So if I go there and back again, it's 0. My displacement is 0 because I'm back where I started. I have not displaced myself anywhere. Okay? I went right back to where I started. My overall displacement is 0. My overall velocity is 0, even though I've walked 8 kilometers total distance. Okay? My displacement ends up being 0 because I technically didn't go anywhere. Right? This is why, if you ever look in your car, it's got a little odometer, okay, that tells you how many kilometers are on your car, how much you've used it. Okay? Does that measure a scalar quantity or a vector quantity? Scalar. It would be totally useless if it measured a vector quantity, because every time you arrived at home, it would read? No, it wouldn't. It would read how far it is from the dealership you bought it at to your house. Come on, people. No one ever gets that right. I trick people on that every time. Okay? Yeah, everyone says 0. No, it would measure the displacement from the dealership to your house, because that's the first trip you ever made with it. Okay? So it wouldn't be very useful then, because it would always reset. It would always go back to that number again. Okay? And it would seem like you've never driven the thing. Right? Which would be great for you to sell it, but it would be totally dishonest. Is that making some sense? So they're looking at the same trip from different points of view. One looks at it in terms of measuring and referencing where you started, and the other is just, what did you do? Okay, so distance and speed are what did you do, not caring about whether you came back. Okay, but displacement and velocity are caring, here's where you started, here's where you ended up, how are they related? Okay. All right, so this is kind of the same idea here. Okay, we talked about that part already. All right, so distance and displacement, this is what we just did on the map there. 2.8 kilometers, 38 degrees north of west. Okay, so you actually have to travel 4 kilometers to get to Walmart, but you only end up 2.8 kilometers in a straight line from where you started. Okay, and then if you come back, okay, like we said, then your total displacement would be 0, even though your total distance traveled is 8 kilometers. All right, questions on that? Okay, so let's look at a simpler example. Let's say that I go 2.0 kilometers, and then I go 1 kilometer, and this is all east except for this, and then I go 2 kilometers west. What's my total distance? That's my total displacement. What's my total distance? 5. I've traveled 5 kilometers. Okay, traveled 5 kilometers because I went 2 plus 1 plus 2. It doesn't care. Distance doesn't care which direction I'm going. But my total displacement, as Scott pointed out, is 1 kilometer. 1 kilometer east. Okay, because I ended up right here. I started here and I ended up here, and those are 1 kilometer apart. 1 kilometer east of where I started. Those are the kind of things that you'll be doing in this course. Okay, all what we call one-dimensional motion. Forward and backward is one-dimensional. Okay, it becomes two-dimensional if you got forward, backward, right, and left. Okay, it becomes three-dimensional if you got forward, backward, right, left, and up and down. You won't ever have to do any of that. Okay, unless you start taking like differential stuff in university. You throw that z-axis in and things get messy in a hurry. Okay. All right. Does Does that make sense to everyone there? Okay, so that's what we'll be dealing with. Up, down, right, left, easy stuff. Okay, formula manipulation. Write this one down, it's not in your notes. Okay, this is just like the mole equation. Okay, V equals D over T. It's a 3-variable formula, which you will not use a triangle for under penalty of death. Okay. We got to go over Mr. Coder's 2.5 rules of algebra. Okay, first rule. To move a variable, do the opposite operation. So if I'm multiplying something, I want to divide it. Okay, if I'm adding something, I want to subtract it. Okay, if you're going to move something, do the opposite. Okay, the second rule of algebra. Okay, what you do to one side, do to the other. Okay, so if I multiply one side by x, I have to multiply the other side by x. Okay, and the half rule. Okay, when moving variables, move what is not attached to the number you're looking for first. Okay, the attached is in quotations. I'll explain what attached means in a minute. You don't have to don't copy that formula down. That's the one I'm going to use to explain what attached means here in just a sec. Okay, so we're going to do the simple stuff first, then I'm going to come back to this whole attached thing. Okay, does anyone need that anymore? Okay. Hey, because I'm pretty sure you guys will have no problem manipulating V equals D over T. You guys didn't have any trouble manipulating N equals little m over big M, so okay, this is very similar. Okay, we'll come back to that here in just a sec. All right, so right now the formula is set up to solve for V. What if I'm given V and I'm given T and I'm looking for D? How do I get D by itself? Jared? Yes, I would multiply V times T. So in order to do that, then I'm multiplying both sides by T, right? Because the first rule was if you want to move something, do the opposite. Right now, I'm dividing by T. So I multiply both sides by T. T comes over here. I've got T times V equals D. All right, everybody okay with that? Mathematically, what I did is that I multiplied both sides by T, right? Now that I have a T on the top and a T on the bottom, they cancel, okay, and the T comes over here. Everyone's good with that? Okay. All right, what if I want to solve for T? Kennedy. Okay, that's what most people say that we should do at this point. And while it will work, it actually doesn't solve for T. I'm going to show you why. Okay, if I divide both sides by D, okay, D cancels, but what's D divided by D? When we say it cancels, we really mean it comes out to 1. So when I go D divided by D, yes, the D cancels, but I'm left with 1 over T. Is that the same as T? No. Okay? It would be like saying 2 is the same as 1 over 2, but it's not. 1 over 2 is a half. Okay? So they're different. So here's what we got to do in a situation like that. Okay? We might have to do a little bit more moving than we initially thought. All right? If you're going to solve for something, it's got to be on the top of the equation. All right? It can't be underneath something. So I'm going to move T over here, like I did before. Okay? Now, is it on the top of the equation? Yeah, there's nothing above it anymore, right? I'm multiplying it by v right now, but that's okay. I'm multiplying it by v. What should I do with v now? If I divide both sides by v, if I got t by itself on the top. Yes, I do. Okay, t is by itself now on the top. So time is distance divided by speed. Now, you can always check to see if you've manipulated something right by checking what units you would get. Right? Let's say that the units for time are hours. This is kilometers. This would be kilometers per hour. So if I divide kilometers by kilometers per hour, what gets left? Hours. So I probably did it right then. Agreed? So if you're ever unsure if you've manipulated something correctly, just check your units and see if you get the right units for what you're looking for. Okay, that's usually the one people have trouble with. Okay, is the one where they're moving something from the bottom, okay, and trying to solve for it. Okay, so we got v equals d over t. If we want to solve for t, we have to move it up first and then bring v over. Okay, everybody all right with that? Okay, so in this formula, there's nothing that's attached. Okay, everything is separate on this formula. But you guys are going to run into a couple of formulas where that's not the case. Okay, I'm actually not going to use this formula first, I'll use it second. This is a formula that you are going to use. Okay, that's how you calculate acceleration. Initial velocity, final velocity minus initial velocity divided by time. All right, I want to solve for VF. Okay, I want to get VF by itself. So what should I move first? What's not attached to VF right now? Right, T is not attached to VF, it's below it. VI is attached. They're right beside each other, and I'm doing something with VI and VF together. That's what I mean by attached. Okay, they could also be considered attached if for some reason I was doing this, which isn't a real formula, but it's just as an example. These two are attached. They're being operated together. Everyone follow on that? Okay, so that's what I mean by attached. Okay, so I'm moving what's not attached first. So if I want to move t, what do I have to do with it? Multiply, because right now I'm dividing by it. So I would multiply both sides by t. T would cancel. T comes over here. All right. I still want to get VF by itself. I've moved what's not attached. Now I can move what is attached. How do I get VI over to the other side? I do the opposite. What's the opposite of subtraction? Adding. Okay, so I've got essentially like negative VI here. So if I go, all right, well, negative VI and positive VI is 0. All right, perfect. That's what I want. Then it can come over here because what I do to one side, I do to the other. Okay, and now I've solved for VF. Okay, is that all right with everybody? As long as you remember those 2.5 rules, you can do all high school science. In fact, you can get through university. I am terrible at math. Okay, honestly, terrible at math. I remember these 2.5 rules. I never got less than 100%, not bragging, never got less than 100% on a university physics exam. The labs killed me. I sucked in the labs. The exams were no problem. Okay, and I only knew 2.5 rules for algebra. Okay, if you can manipulate an equation, you can be successful. All right, and you only need those 2.5 rules to do it. So we're going to spend quite a bit of time in physics working with formulas and kind of polishing up our math skills, okay? Because we got to be able to do that. It's one of those basic skills of science, being able to manipulate, okay? You're going to have to do it in chemistry almost as much as you have to do it in physics. Bio, there's quite a bit less. Obviously, it's not as much of a math-based science, but there is still some, especially when you get to the Hardy-Weinberg population dynamics stuff, okay? There's some formula manipulation that goes in there, okay? So it's in all of the sciences. We got to understand how they work. Okay. So I want you guys to try this problem, okay? If you don't get it, don't worry, okay? Just see how many of you can figure it out on your own before I do it. This is the answer. So if you get this number when you're done, okay, you did it right. So that you could know if you did it right. Yeah. No, I said that. I said, here's the answer, so you know if you did it right. Okay, so let's have a look at this here. Something we need to know if we want to calculate average velocity, okay? And that's the key word here is average velocity, okay? That means over the whole trip. Well, the trip contained two parts, okay? What I have to remember about any average, especially average velocity, is that it is the total displacement over the total time. Okay? So how many of you figured out what its displacement was first? Okay? So that's what you did, right? You went, okay, it went 100 kilometers north, and then it went 62 kilometers south. So its total displacement was 38 kilometers north. Okay? That's the first step. That's what you did right here. All right? You went 100 north and then 62 south, so you figured out this. And then you divided by the total time. Okay? It's just V equals D over T. It's just it was dealing with a whole trip this time as opposed to just one leg of it. All right, so total displacement over total time. So what I usually do on a question like this that has more than one part is I write down my givens. Actually, I do that for every problem. Okay, part 1 and part 2, just so that I know what stuff I have. In part 1, they tell me the displacement in part 1 is 100 kilometers north. They tell me the time is 1.2 hours. Okay, and then in part 2, the displacement is 62 kilometers south, okay, and that takes 0.9 hours. Okay, so I've got all the D's and all the T's, so I can go straight to this formula. Here is what some people try to do, though. Okay, some people will try to go, they'll figure out the velocity for part 1, and they'll figure out the velocity for part 2, and then they'll add them together and divide by 2. Okay, because as soon as they see the word average, they go to what they've used their whole life about calculating averages. Take everybody's score, add them together, and then divide by the number of people, and you have the average. Okay, that's what you've been taught your whole life. The only problem with that is it's only true, it only works if every number you put in there is an equal part of the whole. All right, so in a class, if I'm calculating the class average, every one of your scores counts as an equal part of the class total. Okay, but this trip, the two parts are not equal parts of the whole trip. This first part is considerably more of the trip than this part. If I add their velocities together, I assume they were equal parts of the whole trip, and they're not. This one was 1.2 hours and 100 kilometers, and this one was 0.9 hours and 62 kilometers. It's noticeably less of the trip than this one. So if I put it in the way that we just did here a minute ago, okay, that kind of weights the average, and it makes sure that each part is given its proper weighting over the whole trip. Okay, does that sort of make sense? Okay, so what we do now is we figure out the total displacement, 100 plus 62 south, so 100 north plus 62 south is really just subtracting, okay, and we get 38 kilometers north divided by the total time, 2.1 hours. Right, and when we do that, we should get 18.1 kilometers per hour north. Okay, what if that question hadn't asked for average velocity, but instead it asked for average speed? How would what you did change? Jared? Yes, exactly. Okay, remember that speed is a scalar quantity and doesn't care whether I went north or south. So I would simply go then total distance over total time. And the total distance I travel is 162 kilometers. And then I divide that by the total time, which is still 2.1 hours. Okay? With me there? Yeah? So that's where it's important to understand the difference between a scalar quantity and a vector quantity. Okay, because if I asked you for average velocity on a test and you did speed, you wouldn't get it. You'd get marked for the givens, and that would be it, because after that your work isn't right. Okay. All right, Kira, you look like you needed a question. Did you need to ask something? You're good? Okay. Okay, so just examples here, guys. Okay, examples of scalar quantities. Remember that scalar quantities have magnitude only. They have no direction on them. So speed is a scalar quantity. Okay, distance, scalar quantity. Mass is a scalar quantity. Time is a scalar quantity. Okay, whereas vector quantities have magnitude and direction. So things like displacement, velocity, acceleration, right? Things like that, force, all have direction. Okay, now I'll be photocopying for you a formula sheet here. Probably over the weekend I'll photocopy it so that you'll have that for next week. I don't know, it's maybe got 15 or 20 formulas on it, okay, that we'll need for this unit. All right, now that's why it is so important for you to always write down your givens when you get a physics problem. Right? Writing down your givens immediately eliminates like 95% of the formulas on your sheet. Right? If I'm looking at a sheet that's got 20 formulas on it, and I'm in my question, I'm given a speed and a distance, and I'm asked to find time, I know I won't be using this formula or this one, right? Because I don't have W or F or A, okay? I know these formulas don't apply because that's not what I have. I just got to find a formula that's got what I was given in it, and that's the one I'm going to use, okay? It's like the old Sesame Street thing, right? One of these things is not like the others. Yeah, you got to find the thing that's like all the others. Yeah. Okay. I want you guys to try that one. It's a simple one. It's easier than the one you just did. Okay, deer runs 100 meters in 20 seconds. How fast is it going? Okay. Obviously, for a question like this, you probably wouldn't bother going through all of these steps, but okay. They gave us a distance, 100 meters. Okay. They gave us a time, 20 seconds. How do I know that? Well, I mean, it comes with experience, but when I look at units, meters is always distance or displacement. How do I know in this case it was distance and not displacement? All right. It never said which way. Okay, since it never said which way, I assume it's a distance. It didn't say 100 meters north or south or whatever. All right, time 20 seconds. Time's usually going to be in seconds. Once in a while it'll be minutes or hours. Okay, rarely will it be days or years because we just don't deal with things that long. Okay, V equals D over T. Okay, that's the only formula I can use because A, it's the only one we've learned so far, and it's the only one that has these things in it. Okay, how fast is it going? All right, the question asks how fast is it going? Does it want speed or velocity? Speed. How fast and in what direction would be velocity. Okay. Rarely is a question worded that way though. Okay. Rarely will a question say how fast and in what direction is the object going. It'll usually just say what's the average velocity of the object, right? But if it's wanting speed, it will very often be phrased how fast is it going. Okay. Similarly, if a question is looking for distance, it will often be worded as how far did the object go? All right. But if it's looking for displacement, it would ask how far and in what direction has the object gone from its starting position. Okay, so for this one, V equals D over T, 100 over 20, 5 meters per second. Okay. And most of the time in this course, our velocities and speeds will be in meters per second. Okay. Questions on how that one works? Okay. All right, I want you to try this one. How long will it take a jet traveling at 330 meters per second, which incidentally is the speed of sound, to travel 400 kilometers? Units. Keep something in mind here. Okay. The units for speed were given in meters per second. What do the units for distance then need to be in? Meters. Your units have to match. Okay. I can't divide kilometers by meters. Okay, it doesn't work out. Okay, it's like comparing single oranges to crates of oranges. Okay, they're not the same thing. Yes, they're both oranges, but they're different amounts of it. Okay, so in this question, we were given speed, 330 meters per second. We were given distance, 400 kilometers, which is how many meters? 400,000 meters. Okay, and there's 1,000 meters in a kilometer. In the same way that there are 1,000 grams in a kilogram. Kilo always means 1,000. Okay. How long will it take? How long will it take? We're looking for time. Okay, so V equals D over T, right? And so that's going to be we got to manipulate. Sorry, we're looking for T here. Okay, so what do I have to do with T? I have to multiply both sides by it because I cannot solve for it on the bottom or I'll be solving for 1 over T. Okay, and then I divide both sides by V, and I got T equals D over V. So T equals 400,000 divided by 330. All right, so it's going to take 1,212 seconds, or 20.2 minutes. Okay. All right. Everybody with me on that one? Yeah? What's that? How did you do it differently? What did you turn it into? Oh, okay, so you made it kilometers per second. Okay, yeah, I mean, you could do that too. Yeah. Okay, metric system, something that for some reason doesn't seem to always get beaten to death like it should. Okay, remember that the metric system, and you have this, I think, in the front of your notes package. I put a metric system thing in the front of your notes package. Okay, the metric system is beautiful because it all makes sense. It uses the same prefixes. It doesn't have different units for different types of measurements. Okay, in the imperial system, you got to memorize all kinds of conversion factors. Okay, you got to remember that there are 12 inches in a foot, and there are 3 feet in a yard, and there are 5,280 feet in a mile, and yeah, you got to remember all this stuff, and that there are, what is it, 16 or 8 pints in a, no, 2 cups in a pint, 8 ounces in a cup. You got all these stupid things to remember. Whereas in the metric system, it's always about the prefixes that we add on to this. Okay, so we got our base unit. If it's meters, okay, we're measuring distance. If we got a really big number with meters, we can turn it into bigger prefixes like deca. Okay, a decameter is how many meters? 10 meters. Okay, and we can go up from there, right? Okay, we can go to hecta meters, kilometers, kilometers, not kilometers. Okay, and then you can keep going up. Okay, we got into the metric system. We go up to mega. Okay, giga. Okay, tera above that. All right. Now this is 10 times. This is 100. Right. This is 1,000. Okay. This is 1,000,000. And this is 10 million. No, sorry, it's a billion. Sorry. All right, and so on and so on. Okay, everybody follow me there? All right, so if we go down, okay, if this is an incredibly small number, we might want it to look a little bit bigger, so we can go down and have deci, okay, which is 0.1, okay, centimeters, right, which is 0.01, millimeters, which is 0.001, okay, and then you can go down even further than that to micro, okay, sorry, I shouldn't have the meters on there, just micro. Okay, so we got centi, milli, micro. Okay, and micro is 10 to the minus 6. Okay, and below that there's like femto, and there's all kinds of really small ones below that. All right, the beauty of the metric system is this. Every time you shift up or down, it's a factor of 10. Okay, you never have to remember all those wonky conversion factors that you'd have to remember in the imperial system. Okay, it's always a factor of 10, and it applies to every unit that we use. If it's meters, if it's liters, if it's bytes, even computer memory, okay, is a metric number. Okay, a byte. You got decabytes, hectabytes, kilobytes, megabytes, gigabytes, terabytes. Okay, all depends, and so on. You don't really have fractions of a byte because there's nothing less than a byte. But okay, we could have grams. Okay, basically anything that we can measure, we can put into the metric system and use those prefixes. It's always a factor of 10. Okay, so we do have to know. We got to be able to do some of these conversions like right away in our head. Okay, that's what we got to be able to do. And I'm pretty sure this chart here that I've got above the board. Okay, I'm pretty sure that's in your notes package right near the beginning. Okay. Try that one. Keeping in mind that it gives you direction. Okay, so in this one, we're given not a distance, but a displacement, 650 meters north. Okay, we're also given a velocity, 9.0 meters per second, also north. Would it be possible for these two numbers to have a different vector? No. It would be impossible for you to travel north while having a velocity directed south. Unless you went all the way around the world south and ended up north of where you started. But I mean, that's kind of, we don't deal with questions like that. Okay. There would be, your velocity and your displacement always have to have the same vector. Okay. All right. And in the end, if you had a question where you went all the way around the world and came over the North Pole, because you end up north of where you started, your velocity would be measured north because it would be the smaller number. Anyway, we're looking for time on this one. Okay, how long is it flying for? So v equals d over t, multiply both sides by t, t comes over here, divide both sides by v, v moves over there. Okay, so t is 650 meters north, divided by 9.0 meters per second. North, the meters are going to cancel, the norths will not. Yes, they will. Because time can't be. Yeah, you can't have, it's 10 seconds north. We might say that in North America because we don't talk right, okay? But time can't have a direction on it. All right. So when we do that, 650 divided by 9, right, gives us 72.2 seconds. Okay, 72.2 seconds to do that. All right, everybody okay with that one? Okay, let's have you try this one. Okay, we got an elevator that travels up and then down. We want to find two things, the average speed and the average velocity, keeping in mind that those are two different things. All right, so for the first part, average speed, does it matter whether the elevator is going up or down for that? It does not. Okay, it goes 85, then it goes 60, so we got a total of 145 meters traveled, distance traveled. All right, so for part A, okay, our total distance is going to be 85 plus 60, which is 145 meters. Our total time is 50 seconds. Okay, so average speed is total distance over total time, 145 over 50. What does that come out to? 2.9? 2.9 meters per second. Okay, no direction, speed is scalar. Everyone okay with part A? Okay, so for part B now, okay, I need the total displacement because average velocity is total displacement over total time. Okay, so my total displacement then is going to be 85 up plus 60 down. Everybody all right with that? Okay, which is the same as subtracting it. Whichever way makes more sense in your mind, okay, you can do. For me, I always think vector addition because of what I know is coming in physics. Okay, so my overall displacement is 25 meters up. Okay, does that still take 50 seconds? Yeah, time doesn't change. All right, so that means that we're going 0.5 meters per second up. All right, making sense here? Other than like wording and giving you strange contexts for questions, mathematically it doesn't really get much more difficult than that, okay, for the V equals D over T stuff. Okay, I think there's one more here. All right. This is one of those examples like I just said. Context and just trying to give you lots of numbers to try to confuse you. That would be one like this. Okay, so you still got about 7 minutes left. See if you can do this one. Now, do you have a problem with the units in this question? Yeah, you got hours and you got meters per second. Easier to convert meters per second to meters per hour or hours to seconds? Hours to seconds is the simpler conversion. Okay, so I would say, yeah, convert the hours to seconds. How many seconds in an hour? Everyone wants to say 60, but it's not. It's 60 seconds in a minute, 60 minutes in an hour. 60 squared is 3,600. Okay, there are 3,600 seconds in 1 hour. Yeah, I mean the first part, you're asking for a scalar quantity, or total distance traveled is, we got to figure out how far they go in the first part here, because they tell us their speed, or their velocity, sorry, and how long they walk for. So we got to calculate their distance in the first part. Okay, they tell us the distance in the second, and we got to calculate their distance in the third, and just add those numbers together. Okay, average velocity, okay, is simply a matter of making all of those vector quantities, getting the total displacement, and dividing by the total time. All right, so first thing we need to do is write down our givens. We probably won't get through all of this, but okay, and get them all in the right units. Okay, because what I usually do is I do a lot of calculating about the individual parts first. All right, so our time is 1.1 hours, which multiplied by 3,600 okay, is 3,960 seconds. Okay, and then they tell us the velocity is 3.0 meters per second north. Can I calculate distance with those two numbers? Yeah. Okay, so times 3. All right, so they're going to go 11.88. All right, we'll finish that one up tomorrow. 1,100. There we go. Okay, we'll finish that one up tomorrow.